Okay, our next speaker is Christal Niederer from the Creekside Center for Earth Observation, and she's going to be talking about seeding and transplanting trials of Circium Fontinale variety Fontinale.
Thanks everyone for coming out. I'm excited to talk about this project. It's been a really fun one for us. I am going to mostly use the common name of this taxon, and that's fountain thistle. It is a state and federally listed endangered species. It's also a CNPS-1B2. And it has a very restricted distribution. It's only known from San Mateo County. For those of you who are not local, we are down here at the bottom of the bay in San Jose and Santa Clara County. So San Mateo County is just the next county north as you move up the San Francisco Peninsula. When the U.S. Fish and Wildlife Service wrote the recovery plan for fountain thistle and other serpentine species in the Bay Area in 1998, there were 3 occurrences that were documented. Since that time, 2 of them have been extirpated, but fortunately 2 more have been found in that time. They are clustered around in this area along Highway 280. You'll note that the most northern occurrence has several subcolonies or subpopulations. It's right around the Crystal Springs Reservoir around Highway 280, Highway 92 area. This is a serpentine endemic. Probably most of you know that serpentine soils are fairly uncommon anyway, but this is also found just in moist areas, perennially moist areas in serpentine, so pretty uncommon habitat type. Sometimes it's in actually defined channels, like you'll see right here. More often it's sort of in these open grasslands, sort of these big open seeps where the water is a little bit less defined. And down here we have sort of an odder habitat type where it's sort of an opening in an oak woodland. A little seep found in there. The biology is pretty interesting for this plant. They do not self-pollinate, but they are pollinated by a lot of common pollinators. Mostly our native bumblebee and also common honeybees. And then it has a couple of adaptations that appear to be limiting dispersal. For example, it has a nodding flower head, so the flower heads just sort of nod over, and that's, we believe, is a strategy to keep those seeds going straight down into the wet areas. If they were dispersing too far, they'd probably be going out of those moist areas. The deciduous pappus is a similar adaptation, we believe. So the pappus, probably most of you know, is kind of that dandelion fluff, and you think of a dandelion, the purpose of that pappus is to help that seed disperse far and wide. But if you're a plant that really needs to be in a restricted habitat in that wet area, that's probably not going to be a good strategy for you. So we have this picture down here where every now and again we'll see the seed actually is attached to the pappus, and we'll observe occasionally you'll see a seed floating off, so there's probably a small percentage of the seeds that just sort of go for it and try to go a little bit farther and wider, but for the most part you see the pappus falling off immediately. And so that's probably really limiting the dispersal and making sure that those seeds stay in that appropriately wet habitat that's pretty restricted. Another issue with dispersal, one of the biologists that I work with at the San Francisco Public Utilities Commission, Jessica Appel, has done a lot of research with ants, and she noted that these seeds have elaiosomes. And elaiosomes are sort of these little protuberances on the end here. They're fat and protein-rich bodies. Some people call them ant treats. So if you have elaiosomes on your seeds, then you probably have ants dispersing them. Unfortunately, all of the sites where we currently have fountain thistle have Argentine ants, and probably most of you know that Argentine ants are not native. They're fairly aggressive, and they tend to outcompete native ants. And they're also not known for dispersing seeds. They're a very small-bodied ant. So where you have these Argentine ants, you've probably lost a disperser. There's a lot of threats to the species. Probably a lot of these look familiar. Construction and habitat loss, of course, being very common for most rare species. Non-native plants being a big issue, especially the really big plants like pampas grass, rundo, giant reed, very aggressive large plants. We also have issues with encroachment by native plants. Here's a picture here of a colony. You see fountain thistle in the foreground, and moving into the rest of the wet area here is our native coyote brush. Coyote brush is a great plant in general, but it is very common, and in places where it's pushing out something that is so incredibly rare, it might be something that we want to think about controlling. I did talk about loss of dispersal agents. There are also some seed predators, including a weevil that was introduced as a biocontrol for non-native thistles. Hydrologic changes are really interesting with this taxon. A lot of these colonies that are extant are downhill of Highway 280. Highway 280 was put in the late 1960s, early 1970s, and to protect the water quality of the reservoirs that supply water to the Bay Area. There was a lot of stormwater infrastructure put in with sediment basins, pumps and pipes, all these things. We've had a really hard time figuring out from Caltrans how those were actually built, whether they're being maintained properly or not. This particular population I have the picture of, the source of the water is this rinky-dink little pipe coming out of the side of a frontage road berm. So we sort of look at that and think it just feels very vulnerable. It feels very quote-unquote unnatural, if you will. So a lot of us are sort of nervous about where the water actually is coming from and whether we can feel confident that that water will be coming out in the future and that things won't leak and all that or get clogged up. Climate change, of course, is always the big unknown for everybody as a threat. So in particular, this project came about. The water district, or San Francisco Water, Power, and Sewer, as they're now called, wants to raise the Crystal Springs Dam about 6 feet. And the reason for that is so that if there is a seismic event, that there is more local water storage. Basically, a lot of the water, probably people know, in the Bay Area comes from Hetch Hetchy, so there's a very long system of pipes. Having more water local would be very important in an earthquake. So this is a picture of what's called the boat ramp population. It's a very large population of fountain thistle. You can see them all sort of interspersed in here, and they go right down to the water's edge, unfortunately. So looking at the status of the species, when the recovery plan was written in 1998, they documented about 5,200 plants. In 2011, there's about 40,000 plants documented, and about 30,000 of those were at that boat ramp population that's right next to the reservoir. They counted out 6,341 that were in that proposed inundation area. So that's about 16% of the whole species. That's a pretty significant amount that could be affected by this project. Luckily, there's a lot of low-lying fruit for mitigation for this plant, in my opinion. I think pretty much all of the extant populations are fairly vulnerable to many threats, including invasive plants, scrub conversion, and of course that hydrologic instability that I was talking about. So there's a lot of opportunities to enhance those existing populations. As well as opportunities to potentially create new populations. There appears to be a lot of appropriate habitat that is not occupied, and especially if we think about loss of dispersal agents, they may not be able to get to those places on their own. And I did want to just go to another project we had just to give a little bit of background. This is a project in Redwood City where we had a bunch of arundo in there. Shelter belt builders came in and helped us, or did the removal there. And we went from about 261 plants to 983, so more than tripled the number of plants, but just about doubled the amount of occupied area. And this was all through passive recruitment. So we know from that background that these plants do very well if they're given a fighting chance, if there's a little bit of management that can happen. So with this project, it was sort of a proof of concept for us to see if we could establish new populations. So we started with existing sites to see if we seeded at different times of the year or transplanted different size plants, would that be effective? So we had 3 different seeding treatments, summer, fall, and winter. Summer seeding probably seems strange to a lot of people, but one thing that we noticed when we were monitoring these plants throughout the year, in summertime, where it was wet enough, we were seeing plants germinate. And so I sort of had the idea that perhaps those plants that are getting an early start, as long as it stays wet enough and they don't desiccate, they probably have they may have an advantage that they have roots already established. When you have those, the big winter rains come through, maybe they don't wash away, something like that. So we had 3 different timings of seeding, and then we tried transplanting different sized plants. We also did controls to test passive recruitment. So we had the 6 different treatments. We did them at 3 different sites. Those were all around the Crystal Springs colony. And we had 5 different blocks or replicates, and we did that. We did the planting and seeding in 2 different years. It's just sort of a look at our seeds, a look at what I'm calling a small transplant. Those were plants that the longest leaf was less than 10 centimeters, and the larger ones had longest leaf longer than 10 centimeters. And we analyzed our seeding results differently than the transplanting. If you look at this graph, it's kind of a bummer. We do have fountain thistle coming up in all of our treatments, which is good. However, everything looks very similar to the control, which is not so good. So our seeding did not significantly look different than our control. So we appeared to have a seed bank where plants were popping up. There was really no way to tell whether the plants in our seeded plots came from the seeds that we put in there or were just from the seed bank. But the transplanting was much more effective, and we analyzed this differently because we had a different number of inputs. So we were putting 30 seeds per plot into our seeded plots. These are square meter plots. We were also putting 2 large transplants into our large transplant. So if I had 2 large transplants in a plot, that was much better than 2 little puny seedlings, of course. So our survivorship rate with the large transplants was 88%, which was quite exciting. And with our small transplants, it was a larger or a smaller rate, but still pretty high. It was almost 39%. And the small transplants were a lot easier to do. It's easier to handle the smaller plants. You just sort of pop them out, and they were easy to stick in the ground. So that was very exciting there. We also analyzed survivorship differences by site and had very differential results there. You can see the tall bars are our site at the sediment basin, which was a much, well, I will go over here, was a much wetter site. So the pattern of survivorship was really, can be explained by site moisture, plot moisture. So we had an R squared there of 0.55, which was very high. We did this experiment in 2 dry years. They were below average. We had below average precipitation. We have observed that the fountain thistle colonies, again, they are very dependent on moisture. They seem to expand and contract when we have wet and dry years. And so we were glad that we were able to do this in dry years. We feel like this is a fairly conservative estimate of the success that we might be able to have. So our conclusions were that site selection, especially in regards to moisture, was the most important factor. Transplanting the large plants was the most successful. We had the highest survivorship rate. We also had the highest number of flowering plants. We had 13 plants total flower in our large transplants, and we had 2 in our small transplants. So that was exciting. We did recommend to the client that they do both large and small, again, just because the small ones are so much easier to do and you can do it so quickly. I have no idea why the seeding isn't working. Again, we see the seeds, we see tons of seedlings at the actual sites. They seem to germinate throughout the year. They've germinated in the greenhouse without any special treatment. They don't, they just need moisture. They don't seem to need cold. So anyway, that's a little bit confusing as to why they were not cooperating in our plots. But since we have something that does work, we're not too worried about that. I want to talk a tiny bit about irrigation. We are recommending that irrigation be considered, and not necessarily just for establishing plants. There's sort of a unique opportunity here, since the client is actually the water district and they do these huge water projects. They have said for them it would be fairly easy to establish or enhance a seep and just be able to potentially have something that's long-term, that's installed there. And I think especially since we look at a lot of these existing populations that seem to be very vulnerable hydrologically, or sort of have these, unnatural water sources or questionable water sources, that maybe in this case this might be an opportunity where just actually building something and having that be a long-term water source might be something that's considered. They are planning to do new populations based on this research. There's about 3 or 4 that they're planning to establish fairly soon. They have the permits in place right now. So that's that. I've had a lot of people help on this project. I probably haven't listed everybody, but it's been very fun. Are there any questions?